This is section 15, principle of conservation of momentum of the M1 notes booklet. We're on page 46 of the booklet. As usual, this is a video, so you may need to pause to take notes. I won't pause as I would do in a lesson in order for you to copy up. So please bear that in mind. Now, basically, what we're dealing with in the principle of conservation of momentum, in most cases, is a collision. So when you have two particles of their own masses, m1, m2, own initial speeds, u1 and u2, during a collision, both will undergo a change of momentum. They'll be opposite and equal. So the first particle will have an impulse moving to the left, the second particle will have an impulse moving to the right, and then afterwards, they'll be moving with different speeds than they were initially. So v1 and v2. So the total momentum before equals, so momentum is mass times velocity, so we have m1 times u1 plus m2 times u2. Now the total momentum after can be found in two different ways. So we can look at the after scenario, and it's simply m1 times v1 plus m2 times v2. Or we can apply the impulses to the respective momentums to see how they change. So in the case of m1 u1, the change of momentum is I to the left, so we would take I to get the new momentum. Similarly for m2u2, the second one, the impulse is to the right, so we would add I to change its impulse. But the i's cancel out. Minus I plus I is 0. So we get m1 u1 plus m2 u2, which is the same as the total momentum before. So we've got m1 u1 plus m2 u2 equals m1 v1 plus m2 v2. The total momentum before equals the total momentum. Excuse me. The total momentum before equals the total momentum after. Now in questions, you're just going to need to know that fact. You won't need to derive it from scratch. So, very often, as in many branches of mechanics, it's best to do a sketch to illustrate the scenario. So we've got particle A of mass 2 kilograms moving with a speed of 5 meters per second. Particle B of 4 kilograms is at rest on the surface. So at rest means it has a speed of 0. After the impact, A continues to move in the same direction. So it starts at a mass of 2 kilograms, but with a speed of 1 meters per second. And we're to find the speed of B, which will also have changed. So B, still 4 kilograms, and we'll call that speed V, and that's an unknown we need to find out. So we can use the conservation of momentum formula. So m1 u1 plus m2 u2 plus m1 v1 plus m2 v2. So to put the numbers in, 2 times 5 plus 4 times 0 equals 2 times 1 plus 4 times v. So we have 10 plus 0 is 10 for the left hand side, 2 plus 4v on the right hand side. Take 2 from both sides. 8 is equal to 4 times v. Divide by the 4. V is 2 meters per second. So same sort of idea, particles P and Q this time. And they start, they've got mass 5 kilograms and 8 kilograms. They're moving towards each other with speeds 3 meters per second and 2 meters per second respectively. After the impact, the direction of P is reversed and its speed is 1. Still has a mass of 5 kilograms, and we're to find the speed of Q. Now it didn't say which direction Q is going in. We can just choose a direction, and then if we get a negative answer, we chose the wrong direction. So as long as we're consistent with the equations, it won't matter, we can just interpret the answer. And V still has a mass of 8 kilograms. So the conservation of momentum, m1u1 plus m2u2 equals m1v1 plus m2v2. Stick values in, 5 times 3 plus 8 times, and this is where we have to be careful, these are velocities not speed, so direction matters. So if we're making right positive, which we have by making it plus 3, 2 is going to the left, so it's minus 2 going to the left. And this is a key point, this is where people tend to make mistakes in these sort of questions. So if we make right positive, left must be negative. Equals 5 times, and again, it's pointing to left, so it's minus 1 and not just 1, plus 8 times V. Calculating, we've got 5 times 3 is 15, plus 8 times minus 2, 15 minus 16 is minus 1 for the left hand side. 5 times minus 1 is minus 5, plus 8V. Add 5 to both sides, 8V is equal to 4. Divide both sides by 8. And V is equal to 0.5 meters per second. And if we've got a positive answer, so it means that the direction it's going, Q is going in, is right. If we'd got a negative answer, it would have really been going to the left. So we would, and since we've been asked for the speed, we would need the next line saying speed is the positive value of it. So a slightly different one. So we've got a snooker ball P hits a stationary ball Q. So P was moving at speed 8 meters per second. Q was stationary, so no speed. And they have equal mass, but we're not told what the mass is, so we'll call the mass M. Afterwards, we're told the speed of Q is twice the speed of P, but no actual values. And they're still moving in the same direction. So, let's call the speed of P V. And then the speed of Q is twice that of P, so it would be 2 times V. And then we can apply conservation momentum formula again. So m1u1 plus m2u2 equals m1v1 plus m2v2. So sticking values, 8 times m plus 0 times m, which is 0, equals m times v 2 times mv, 2 times mv. So right hand side, well, left hand side becomes 8m, right hand side becomes 3mv. We can cancel down by the m's, divide by m both sides. Divide both sides by 3. We get an answer of 2 2/3 meters per second. Right, and last, another thing we can use conservation momentum for is the idea of jerking the string. So here we've got P and Q are attached by a string, and at the moment the string is loose. Then we might project Q away from P. So at first only Q is moving because the string isn't tight yet, so P would stay stationary, but the string would keep getting tighter and tighter and tighter. At the very point where the string pulls fully tight, it will jerk. So force P to start moving towards, and it will drag back on Q. Now in this case, the conservation momentum also applies to enable to calculate things. So before and after, again, so we've got 2 particles, P and Q, connected by a light extensible string, initially slack. So that's just to say that the string has no mass, and we're not going to take its weight into account. P is projected away from Q, so to get this scenario the right way around, we'll put Q on the left and P on the right. And P is projected away with a speed of 5 meters per second. And Q will not be moving at that point. Now P has mass 6 kilograms and Q 4 kilograms. Afterwards, after the point where the string jerks and pulls tight, they'll move at a common speed. So that what we're asking for here is, first of all, is that what is that common speed? So I'm going to call the common speed V. So there's a link here with connected particles. So again, conservation momentum formula. So we have 4 times 0 plus 6 times 5 equals 4 times V plus 6 times V. So simplifying, left hand side calculates to 30, right hand side, collect like terms, is 10V, divide both sides by 10, and V is 3 meters per second. Now to find the impulse in the string, well the impulse, we'll just want one of the impulses. The impulses would be opposite, equal and opposite for the 2 particles. So we just choose a particle P or Q and we calculate the impulse for that. So Q seems simplest. But we could just as easily have used P. So impulse for Q. Impulse is a change in momentum for Q. So basically one should give us a positive answer, one should give us a negative answer. And usually you ask for the magnitude of impulse, so in those cases you would ignore the minus. So in this case, V is 3, so 4 times 3 minus 4 times 0 gives 12 Newton seconds. And that concludes this session.